Rock is solid matter that can be made up of a combination of minerals, fragments of other rocks, or the remains of plants or animals. Scientists classify rocks into three main types: igneous, sedimentary, or metamorphic. Igneous rock forms when molten rock cools and solidifies. Intrusive igneous rocks, such as granite, form from magma, which is molten rock underground. Extrusive igneous rocks, like basalt, form from lava, molten rock that erupts at Earth's surface. Sedimentary rock forms from accumulated deposits of pre-existing rocks, minerals, or the remains of plants or animals, resulting in rocks such as coal or limestone. Scientists have found pollen grains trapped in sedimentary rocks that are tens of millions of years old and are able to use those grains to decipher the vegetative and ecological state of Earth at that time, and also to make predictions about how the next chapter of Earth's environment might read. Metamorphic rock has undergone structural or chemical changes caused by an increase in heat, pressure, or by the replacement of elements by hot fluids. Marble and Acosta gneiss are examples of metamorphic rock. Acosta gneiss is a critical storyteller of our Earth's history because at about 4 billion years old, it is the oldest known exposed rock, holding clues about our early Earth that we are hard-pressed to find elsewhere.
Welcome to the JASON Project, where we're taking an in-depth look at igneous, sedimentary, and metamorphic rocks, and how these rocks influence our daily lives in ways beyond our wildest imaginations. Our experts and teacher Argos went all around Texas, from the Big Thicket to 1,600 feet below the Earth's surface in a real salt mine. Now, let's go find our experts and teacher Argos and see what they're up to.
Best part about my job is blowing stuff up. It's a childhood dream and I get to do it.
Best part about my job is getting salt to our customers and making them happy. What's interesting about my job is dealing with production, making sure that the salt is produced in bags, in blocks, so that we can get it to our customers on time. Getting it booked with our truck drivers, dispatching, those kinds of things.
We say safe. I'm the one make sure everything is safe to everybody be safe. It's kind of interesting because, if you're not safe, you can risk a lot of lives and everything. So it's the most important job.
The best thing about my job is watching kids learn and seeing the lights come on, them understanding a concept, seeing things in nature that they finally understand why that's what's happening. That's fun. It's also fun to have kids come back years later and still talk about what they learned in science class and how they're using it in their lives lots of years later.
I learned that salt is constantly moving, and I was quite surprised that it moves at a faster rate than I had originally thought. Oh, my favorite part of my day would be the feeling that you get when a student has that aha moment, and it's great when you can bring in real-world experiences into the classroom and introduce something that a student may never get to experience or hasn't experienced yet. And so that's probably one of my favorite parts of my job.
Favorite part of my job is I have lots of jobs to pick from. But one of the favorite jobs I have is being a research paleontologist and be able to go out camping, out to get away from the city and find fossils of things that nobody's ever seen before, things that have been buried for millions of years. And because of our work, we're keeping them from being destroyed by natural weathering and actually able to salvage them and bring them into study.
Well, I work at the business center quite a bit, and I get a lot of people from all over the world coming through. And I like to talk about the Big Thicket. I like it because of the diversity that we have here, and you also have people coming in all over the world, and you can be surprised how much we are alike, and how the diversity of people from Europe and Asia and Africa and come in, and they have common things to talk about. And that's one thing I like about working in the Big Thicket. And to get children involved at school, it's not very difficult. And it's great to see their eyes open up, and once you get them involved and interested in the Big Thicket or in nature, and to be a steward of all this, to work outside. I teach art, and you know how artists start, they're kind of a little different. Anyhow, I tend to like the sleuths. You go down there at night, right at dusk, right before the sun goes down, and it's just really creepy, cool. And sometimes you can see fall coming up this time of year, and the bats come out, and I really like that part of the Big Thicket, the cypress sloughs, and just getting closer to the watershed down there, the Village Creek. That's one of my favorite parts.
My favorite part about being a park ranger is being able to get away from my desk and enjoy the out of doors and nature. And beyond that, to share it with people. I'm amazed at how many people really don't get out very often, and I think that's something that brings a lot of perspective to our lives in this urban world that we live in. I like to get students interested in national parks by first doing field trips with programs like JASON. And beyond that, at the college level, we love to have interns, and I like to mentor young students and get them interested. I think a lot of students don't realize that not only are there botanists and scientists positioned, there's law enforcement, there's maintenance, there's budget, there's administration, and it's all not natural either. The National Park Service manages and protects cultural sites as well. So if you're an historian or an archaeologist, the National Park Service has got something for everybody, really.
Or they finally are beginning to piece together parts that they have had prior to coming to me, or being a part of the JASON Project, where we can be outdoors and explore different aspects of the science and not just be in the classroom, but do hands-on on location. I think it helps enrich my own learning, where when I take it back to the students, it's new and exciting, and I can get them involved in programs where maybe it'll spark a little more interest than they might have normally.
Welcome to Lamar University and this year's JASON event, Operation Tectonic Fury.
I'm Evelyn Thomas from Odom Academy in Beaumont and an Argo co-host.
I'm Brandon Shang from Marshall Middle School, your other co-host.
Today's missions will include an underground visit into a salt mine 1,500 feet under Huckley, Texas.
Then we will explore downtown Beaumont and learn how to recognize the types of rocks that make up our buildings.
After that, we will see how soils are formed through rock weathering and how different soils affect the forests in the Big Thicket National Preserve.
Then we will go to Rollover Pass to solve the mystery of Rollover Bay.
Finally, we will visit the fossil exhibits at Houston's Museum of Natural Science and find out what the remains of ancient animals tell us about the age and history of our planet.
But first, we need to find out what geology is and why it's so important to Texas.
Hi, I'm Carla Tucker, a geologist and an instructor in the Earth and Space Sciences Department at Lamar University. This year, JASON's Operation Tectonic Fury is all about geology. Geology is the study of the Earth, its 4.5 billion year history, and its physical resources. Here in Texas, our geologic history extends from beach deposits that are forming today all the way back to billion-year-old rocks exposed near Fredericksburg. This long geologic history has given Texas some fantastic geologic resources which we use every day and are a foundation of our state's economy. One of the most important geologic resources found in Texas is groundwater, which is my specialty. Half of the water used for agriculture, for industry, and for our municipal water supply comes from groundwater resources. Rains, streams, and lakes provide us with the rest of the water that we need. Texas is also lucky to have crude oil and natural gas deposits. The wells that tap these reservoirs supply us with energy worth billions of dollars each year. We also get energy from coal. In East Texas, there are coal mines that produce millions of tons of coal used to generate electricity for our homes and schools. And we have quarries across the state that provide us with building stones, such as this pink granite, and we have mines that come up with clay that we use to make kitty litter or bricks for our houses. There's also quarries of sand and gravel and Portland cement, which hold our roads and buildings together. If all this sounds interesting, then I bet you'd like to go 1,500 feet underground into a mine near Houston that blasts out ancient Gulf of Mexico salt that can be used for our livestock, and we also use it to make homemade ice cream. So let's head down into the mine and go back to the Jurassic.
Texas has mines of all kinds all over the state. But today, our Argos are going from Beaumont on through the west of Houston to the Hockley Salt Mine to learn what goes on underground.
I teach at Odom Academy in Beaumont.
And I teach at Regina Howe Elementary in Beaumont, Texas.
I'm the mine superintendent of the Hockley Salt Mine located here in Hockley, Texas. This morning we went for a tour. We got to see various processes that we go through in order to extract our salt and get it to the surface to put in the truck to sell it. Our mine is 1,550 feet deep. We're led to believe that the actual salt dome itself could surpass 30,000 feet in depth, which is roughly 6 miles of a 2-inch diameter dome 6 miles deep into the earth. From the research I've done, they're telling me our salt deposit is roughly 250 million years old. Not real sure. The geologists are kind of on the fence, could be plus or minus up to 350, but they think the salt was deposited here as a result of the Gulf of Mexico receding, leaving the evaporated salt here, being overlain with years of sedimentation, being compressed, compacted, and pushed up through a weakness in the earth, which gave us the Hockley Salt Dome.
I think the most exciting thing that I saw was halite actually in its natural state. We've all seen rock salt and pieces of salt, but I had never actually seen it in the ground like it was.
It's a mineral. I'm not real sure why they call it rock salt, other than the fact that it was considered halite. Rock salt became the common name for halite. The first part we do is we drill. We'll drill approximately 11-foot deep hole. About 10 foot of that will actually explode. It is filled with ammonium nitrate and fuel oil, which we call AMFO. We will tie each one of those holes together at approximately 155 per face, tie them together with light line, and approximately 500 milliseconds, the entire show will be over. We will have one shot face of approximately 1,200 cubic feet of salt. After that process, we will come in with our front end loader, which is a Volvo L120F. We'll take approximately 4 to 5 scoops of it, load it into our Volvo A30D haul truck. He will then take it from there, go to the crusher. At the crusher, we take the big chunks, put them down to about 2 inches in size to go to our surge pile on our project. From the project, that 2-inch piece of salt will go down to about a 1/2-inch piece of salt. From there, we'll go into our screens where we will separate off our 4 main products: coarse, medium, stock, and feed mix. Those 4 products will go out through various belts onto a pile to wait for the customers on the surface to tell us which product that they would want. At that time, we will ship the product out to the surface, put it either into a bulk truck, put it into bags, or use our stock salt and make blocks.
We supply salt primarily to agricultural dealers. We supply to feed mills, and we supply to anyone who has animals or livestock that need salt licks, salt blocks, those kinds of things. We also do quite a bit of business with the oil field, and in the wintertime de-icing, which goes through our Chicago distribution up to the states in the north.
I also learned that it takes very little explosive to clear a portion of the mine.
Our explosive, we use ammonium nitrate and fuel oil. They're mixed according to a certain recipe, which we won't get into. But they will take the ammonium nitrate and the fuel oil, mix it in the truck when they come out here. They come separate, they mix them here, we send them underground. At the face, we will use, it looks like a big sandblaster tank, to inject the hole and the cap, to inject the AMFO and the cap into the hole, then tie them all together. That process, we have our lift machine that you saw. What we'll do then, we'll tie them all together, and then we'll shoot from outside. We'll turn 2 keys, the explosion will go off in about 500 milliseconds. Roughly. But that ammonium nitrate and fuel oil with the detonator will cause a lot of gas to be produced, and that gas is what we utilize to push the salt from the face out to break it.
I thought one of the neatest things was after we went all the way down the 1,600 feet or so in the elevator, to see the huge trucks and equipment down there and to find out that it went down the same elevator we did. It just had to take it apart and then put it back together on the mine floor.
Our shaft is specific size of 5 foot by 6 foot. Every piece of equipment has to fit inside that size. So if it does not fit, we will take the torch or hand tools, dismantle it or cut it, ship it, reassemble it back underground and weld it back together. Salt mining is very safe. I would say it's comparable probably to metal mines, maybe a little safer than metal mines, but much more safer than in the coal mines. The coal mines have a lot of inherent, I guess, deficiencies with the structures that we do not have. Salt is self-supporting. It will support itself, so we don't do roof bolting. We don't have the methane. We don't have the water. It's just a lot less of the environmental variables to contend with we don't have.
I'm like maintenance on a heavy machinery. I do the gas reading order like at 3 o'clock in the morning, twice a day, 3 in the morning, 1:30 in the afternoon. Well, this is a gas detector. You go by this over here. If you say safe, you safe. If you don't, you gotta go up.
What we do for ventilation, I kind of like to use a picture of ventilating a pop bottle. What we did was we've created compartments to put good air coming down in, the used air coming back out the other side. So if you can kind of visualize it, we've set up partitions so that certain air won't go certain places. By setting up those partitions, it set up a flow so that the good air will go through to the face, ventilate the face, come back around as used air, and come back out to the surface.
I was really excited to go because I've never been to a mine or a cave or anything of the like, and I was quite impressed with the organization and the efficiency of the tour.
So these salt blocks that help feed cows all over America and keep them healthy, and this rock salt that helps keep snow and ice off our highways in winter, is mined deep underground near Houston from geologic deposits that were formed hundreds of millions of years ago when dinosaurs still roamed the earth. And that's why geology rocks. Hey, here's a question. I hope you've been paying attention because I need an answer. What created Texas Jurassic Age salt deposits? Is it A, volcanoes? Is it B, the Gulf of Mexico? Or is it C, river deposition? If you think you know the answer, put your finger on your nose now. The correct answer is B, the Gulf of Mexico. And hey, you in the third row, I said on your nose, not in your nose. Let's see what we can learn about rocks by looking at the buildings in a typical city. Our student Argos and teachers took a journey through downtown Beaumont to learn how to identify rocks by looking at their texture and mineral composition. At their first stop, the Argos discovered that the Jefferson County Courthouse Annex building is made of igneous rock, which is formed through the cooling of hot magma or molten lava.
When it's deep down, then it kind of contains the heat, so it allows it to cool off slowly, so that it allows the crystals a long time to grow. So how do we know that these are crystals and they're not pieces of sediment that have been moved from one place to another?
They're very jagged around the edges.
They haven't been transported or weathered because the edges are angular. They have sharp edges. If they'd been transported, they'd be round. Okay, so we have interlocking crystals. Okay, we have two different classes, two different ways that we can describe crystal size. We have fine grain and we have coarse grain. So would we describe this as being a fine grain or coarse grain?
It'd be a coarse grain because they're big enough to see. Fine grain, you have to have a microscope to see.
And so we have a special group of coarse grain rocks that when the crystal size is bigger than the centimeter, then we call it what? Very good, pegmatite. And then we have another way that we can describe this rock, okay? We have two groups. We have felsic and we have mafic. So felsic is going to be a light color, mafics are dark. So would you even describe this as felsic or mafic?
Felsic.
I describe it as felsic.
Okay, we would describe it as felsic. So do you guys know of a possible igneous rock, okay, that is coarse grain and that is felsic? We would call it a what?
I'd say granite.
So this would be called a pegmatite granite. Pegmatite because of the grain size, and then granite because of its chemical composition.
The second stop on our tour was the Jack Brooks Federal Building. Here, the Argos use a test to apply acid to this rock. When the acid fizzes, they learn that the mineral calcite causes the fizzing. Rocks composed of calcite are called limestone, which is a sedimentary rock.
So it's rough, it has that rough texture, okay? So if it's a sedimentary rock, but it's not a clastic rock, so it's not like the sandstone because it does fizz. So why do we call a sedimentary rock that fizzes when we put hydrochloric acid on it? Awesome, very good. We call it limestone.
Oh.
Okay, now we're going to move over here to the steps where we find still another type of rock. We have some banding going on. It kind of reminds us of the granite because we can see we can see some dark minerals, and we can also see some light colored minerals. And so what could cause a granite to form layers in it? Because the other granite didn't have layers in it. So is this granite?
No, not anymore. Used to be white granite, now it's nice.
Very good. How did it change into nice?
It went through a metamorphic process, which makes it a metamorphic rock.
Very good. So it was granite that's been subjected to heat, pressure, maybe chemical alteration, and so it's no longer granite, and now it's a new type of rock, a metamorphic rock called granite gneiss. What do we call sedimentary rocks or rocks that are made up of bits and pieces of particles? Plastic, very good. We call them that they're plastic, and we generally name them according to the size of the particles. These particles are what size? How would you categorize it?
Sand, very fine sand.
So if it's made out of sand, it's going to be called. What if it was made out of clay?
It'd be clay stone.
What if it was made out of silt?
Siltstone.
Very good. So you are absolutely right. So we could classify this as a sedimentary rock, and it would be a clastic sandstone.
To learn more about sandstone, the Argos visited the Temple of the Brave in downtown Beaumont. This awesome building from the 1930s is made of sandstone, and the Argos explored its composition to answer some important questions.
Okay, so what types of rocks are made from pieces and parts of things?
Sedimentary.
Do you see anything else that stands out that makes you think that it was, you said you thought it was a sedimentary earlier, so any other indicators why you think it's a sedimentary rock? What are some other indicators? How did it feel when you touched it?
It's kind of rough. It's
Kind
pretty
of rough. Kind of
Like
like what?
sandpaper.
Kind of like sandpaper?
So what type of rock do you think this is?
Sandstone?
Very good. Sandstone.
The last stop on our tour of Beaumont Rocks was the Terrell Library, which looks like an old castle, but the rocks that built it are much, much older than any castle on Earth.
And once again, we're going to perform our first test, our acid test. And let's see if we have some reaction. Do you see anything in this rock that we haven't seen in the other rocks?
It's like a bunch of shells together.
Okay, we see a lot of shells. So if we find fossils in a rock, then we know it's going to be a sedimentary rock. Very good. We've already said this type of sedimentary rock that fizzes when we put hydrochloric acid on it is what? Okay, it contains calcite. Very good. And what type of rock was it? Very good. It's limestone. So a type of limestone then that has fossils in it, what do you think we might call a limestone that has fossils in it?
Fossilized limestone.
Very good. We call it a fossiliferous limestone. Very good. We can also use the age of the fossils if we can identify the fossils. So, for example, if we can find an organism and then we can identify it, we can also then determine the age of the rock. And so if you had to take a guess, how old do you think these rocks might be?
3 million years.
3 million years?
About
1,000? What if I told you about 300 million years? So these rocks are actually Paleozoic in age, probably formed during the Carboniferous period.
I learned how to tell the difference between several types of rocks and the characteristics of 3 types of rocks, which is igneous, metamorphic, and sedimentary. Well, igneous has crystals in it, and the crystals kind of jagged edges, but they ain't been transported, and they're just formed together. And metamorphic, you can just tell it's went through several changes. And sedimentary you can tell because it has different layers and it has made up of particles.
The sedimentary rock weathers the most because it weathers into sediments.
The green rocks, they were deeper down in the water and they weren't exposed to oxygen. So whenever they were, I went through a process called oxidation.
The favorite part today was when we was testing to see if it fizzed or didn't fizz and see if it had any calcite and like to see if it was limestone, like the tail part right here.
They're finally taking a closer look at the things around them. So that's the favorite part of my job. Taking them out in the real world, getting their hands dirty, kind of thing.
Science is just so cool to teach because everything's different, everything's new. You can always expose the kids to something new and different.
Hey, it's me again. I've got a question and you've got an answer. How fast did igneous rocks with large crystals cool? Was it A, instantly, B, quickly, or C, very slowly? Go ahead and take a second to think it over. The answer is C, very slowly. And I hope you weren't slow with that answer. Our journey with the Jason Project takes us to the Big Thicket, which is about a 40-minute drive from Beaumont. And here we're going to see headstone spoils and Big Thicket soils.
Welcome to the Big Thicket. In the Jason Project this year, we're talking about soil, how soil is formed, and how that reacts with the different ecosystems. The reason why some of the plants and animals have gotten here and are so widely distributed is because of soil. We will go into 2 different areas. We'll be going into an upland area. We'll test the soils. You'll be able to compare and contrast those soils to a wetland area. And I hope that by the end of the day, you'll be able to figure out why the soils affect the distribution of the plants and animals that make Big Thicket so famous for biodiversity. This is the slope forest that we're in.
First things first, the Argos test soil properties with their sieves.
We're looking at soil texture and the size of the particles. That makes a difference. This is pretty fine particles here. This is is it gritty? Feel of it.
High quality stuff.
Yeah, that's what we would call silt. What is silt?
Silt is fine grains of earthy matter carried by running water and deposited as sediment.
We want to know how quickly the water gets down to that hard
And
pan.
just how does it get there? Through percolation, of course. Percolation is the slow movement of water through soil or permeable rock. Through this experiment, the Argos will first need to establish a constant.
What's a constant? We'll ask. When you're doing this. Huh?
Something that doesn't change.
Something that doesn't change. So if we're doing 100 milliliters here and we want to compare it to the next site that we go to, it needs to be the same. That's your constant.
Timing how long it takes for the water to percolate will give you the rate of percolation. Next, the Argos test the acidity of the soil. To do this, the Argo places the pH reader into the soil.
What'd y'all get? 6.5. So we know that it's definitely above 6.5 or 6.5 or above. Does anybody know enough about pH to know what that means?
The pH scale measures how acidic or how basic a substance is. The pH scale ranges from 0 to 14. A pH of 7 is neutral. A pH greater than 7 is basic, while a pH lower than 7 is acidic.
So because we're below 7, what does that tell you?
More acid in our community.
We got a little bit of acid in our soils there. And that's good for plants. It's good for some plants. Some plants can't take it at all.
Next, the Argos perform a moisture test. Just like last time, they'll use the reader and wait for the results.
What we're reading on the bottom is the percentage of moisture in the soils. And so it went down to about, I can't read that from here. It looked like it was just above the 0. So I'm thinking, 10% or less. It didn't move much. Bagel could be on the highest part of land. It's like just a little bowl.
So kind of like a little pond or a lake.
That's right. And the water runs down into it and just sits there. It doesn't go anywhere. Typically, we would not be able to do it here because this is underwater. What are we looking at in composition? What'd you get in your trays there? Okay, there's a lot of detritus or mulch or organic plant material. What are we measuring here? A percentage of water, which usually is really directly related to percolation. What's it read? 70% moisture content. What does that tell you? Okay, it's lower area, that any water that there might be in the soil is drained down here.
Hey, let's review. The Argos experimented with many properties of soil, including pH, moisture levels, soil composition, and percolation rates. When comparing the soils from two areas, the Argos found that the soil can be all sorts of shapes and sizes. Now that they've completed the results, the students meet up with Dr. Westgate at a local cemetery.
Well, around here, the only way to generate new soil is to weather and transport old soil. But this original soil didn't start here, it came from somewhere else. And if we want to talk about how rocks weather, that means we have to go to a place where rocks have been brought to us. So these aren't native Southeast Texas rocks, these are rocks that have been transported to the area. This is dilute hydrochloric acid, and if the minerals fizz, that tells you they're made out of the mineral calcite. So what's happening?
Nothing.
Nothing.
Okay.
It's sitting there.
Yeah, so no reaction. So what does that tell you about how much calcite is in that granite?
Not much.
None.
No calcite in the granite. This rock is marble, and marble's made out of calcite, which has calcium and carbonate together. And when you put the acid on it, it fizzes. So, and this is just 10% hydrochloric, so weak acids will make this rock dissolve. Okay, so does that give you any clue what has happened to this marble stone?
Acid rain.
Yeah, so we have rain is always acid because carbon dioxide's in the air. Rainwater absorbs that carbon dioxide just like Coca-Cola, and when it rains on marble, what's going to happen to it through time?
It's going to degrade.
Yeah, it's going to dissolve. How much chemical weathering has occurred to this compared to that marble?
Whoa, wait a minute! Chemical weathering? What is that? Chemical weathering is the breaking down of rocks and soils by chemical reactions.
There is some chemical weathering going on here though, and if you look Notice anything? You know, the rock is white and gray, but there's some green stuff on here. Any idea what that is?
Lichen or moss?
Yeah, those are lichens. And lichens are colonizing this even though there's no soil. So some organisms can actually grow where there isn't any soil, but by their activity, they're creating soil. Anybody have any idea what mineral this is?
Quartz.
Could be quartz. See if, why don't you do a hardness test? See if you can scratch that with my key.
It's too glassy.
Okay, so those minerals are harder than my key, but the big white crystal is softer. So it must not be quartz. So see if you can taste it. Does it have any taste?
It's salty.
Where do you think the sodium and chlorine atoms that made that crystal came from? Originally granite, but before there was an in-between, it didn't go straight from granite to salt crystals.
Body of water.
It went to the Gulf of Mexico, and then the Gulf of Mexico evaporated partly and left that behind.
So, what did you like about today?
I liked going into the Bay Galls and learning how they don't have to be necessarily at like the bottom of a hill. They can be up in the peak of a hill, just as a depression in the hill. It seemed pretty neat.
My favorite thing about today was sieving through the soil.
I think my favorite part was, part of it was sifting through the soil and part of it was making mud pies and getting salt.
I learned today that sodium chloride is salt and that calcite is in the salt.
I like to get students interested in national parks by first doing field trips with programs like JASON.
I think it helps enrich my own learning, where when I take it back to the students, it's new and exciting, and I can get them involved in programs where maybe it'll spark a little more interest than they might have normally.
And to get children involved at school, it's not very difficult, and it's great to see their eyes open up, and once you get them involved and interested in the big thicket or in nature.
I'm amazed at how many people really don't get out very often, and I think that's something that brings a lot of perspective to our lives in this urban world that we live in.
Question time. Raise your hand if you're ready. That's what I'm talking about. Here's your question. Acid makes marble fizz because it's made out of what mineral? Was it A, calcite, B, halite, C, quartz, or D, none of the above? The correct answer is A, calcite. And if you knew the answer to that, pat yourself on the back. You did a great job. Next stop, rollover pass. Our team of Argos and expert Cindy Parrish will try to solve the mystery of how beach sand is being deposited in the bay. Let's catch up with them and see what they've discovered.
Okay guys, where are we?
We're at the Galveston
Rollover Pass. Okay, Rollover Pass. So Evelyn, where do you think we are on that map?
We are
right along here. Okay. So, Zach, if we look at this map, what do you notice about this? Does this look natural or is it unnatural?
It does not look natural.
Why not?
Because it's like got a big gash in the middle.
Okay. What else do you guys see?
It's perfectly aligned.
Okay. So it's a straight line. Is that natural? No. Okay. So what do you think they did here?
They artificially built a bridge over where they insulated between the Rollover Bay and Rollover Pass.
Let's see, is the tide coming in right now or is the tide going out?
It's coming
in.
Here the Argos see the flooding tide just starting to rise. But even though the water is rising, it'll take about 8 hours before full high tide. Tides are the rise and fall of sea levels caused by the combined effects of the rotation of the Earth and the gravitational forces exerted by the sun and the moon. So, how do we know when the tide is high?
The water is coming closer to the land.
According to the map, the tide is coming back in. and that means the water level will rise until the tide reaches its highest level. And the Argos will find out exactly when that is.
So what time is high tide?
11 o'clock.
Okay, what time is that in military time?
2300.
Okay, so why don't we just say 11 o'clock?
Because when you're going by tides, you go by military time.
Okay, so we don't get confused with AM and PM?
Now that we know where we are on a map, let's see what the GPS reading for our location is.
We're at north 29 degrees, west 94 degrees.
What do you think our elevation is, just looking around?
About 10 feet above sea level? 5 feet.
Maybe 3 or 4 feet above sea level, maybe right here? Where is sea level?
Where the water is.
Where the water is. Great job.
The Argos now test the salinity of the water. Salinity is the degree of saltiness of the oceans, seas, lakes, and rivers, usually expressed as the number of parts per thousand, or the weight of salt dissolved in 1,000 parts of water. In other words,
When you measure the salinity, you measure the salt in the water.
the purpose of checking salinity on the bay is so that the result can be compared to the salinity in the Gulf of Mexico. Here, Evelyn brings water in a large container so that Jeremy can check the salinity.
Okay, and what are we reading here?
How much salt is in the water?
Okay, so what is your reading?
24.9.
Okay, 24.9. It's kind of moving up and down, isn't it? Okay, what's our temperature of the water?
18.6 degrees Celsius.
Okay, so is that cold or is that warm or?
Cold.
Okay, so the water still feels cold, doesn't it? Okay, so 24, is that normal salinity or do you know? You don't know yet, do you? I guess we'll have to go test it on the other side and see what the salinity is in the Gulf of Mexico.
The team will now take a look at a sediment sample. Normally, in the bay, mud deposits are found, but here at Rollover Pass, sand is being deposited due to the artificial cut. Testing the sediment will allow us to see if what is found has more mud deposits or more sand deposits.
Okay guys, let's come look at this sediment that we got in these sieves. Okay, which one of these has got the most sand in it? Let's look. Okay, let's look. Okay, I'm gonna hold, you can set it down if you want to. You got your hands free. Okay, let's look and see. Okay, so these two that are on the bottom, okay, which one do you think has the most sediment in it? This one has the most sediment in it? Okay, this says that it's 500 micrometers, and this one says that it's, what does it say on this side?
Kind of covered up. 180.
180 micrometers. Okay, so we've got very fine sand, right? That doesn't really look muddy, does it? Okay, most of the time in the bays in Texas, you have mud in the bays. So why don't we have mud here?
It's because the flow of the water comes through, it goes faster, and water is cleansed by the sand.
Okay, well most of the time in a bay, do we have water coming in from the Gulf? No, we don't normally have water coming in from the Gulf, do we? That would actually put sediment in, so it would deposit mud. Is mud smaller or bigger than sand?
Smaller.
It's smaller, isn't it? Okay, so the mud grains are actually smaller than what the sand grains are, and so you've got a different kind of deposit here. I wonder why that is. You think it's because of the bay being behind the cut?
It's possible.
Okay, so we've got an artificial inlet that's coming into the bay and it's bringing sand and sediment with it. Let's go look at the sediment on the other side and see what it looks like.
The team of Argos goes to the other side of the artificial cut, along with expert Cindy Parrish. Here at the Gulf of Mexico, they test their hypothesis that sand is being deposited into the bay because of water coming in from the Gulf through the artificial cut. To test this, they throw water balloons into the water. These water balloons float on the surface because they're filled with fresh water, which is actually lighter than salt water. This allows them to determine which direction the longshore current is moving. But hey, what is a longshore current? Longshore current is the movement of water along a coast parallel to the
So our
shoreline.
balloons came on shore in about 3 minutes, and that's about 300 feet in about 3 minutes. So how fast did it go? Okay, that's 100 feet per minute.
Sediments, usually sand, moved by the current are called longshore transport. Sand moved by waves breaking on the beach is called littoral drift. Let's find out which direction the current is moving.
Okay, guys, so when you threw the balloons in the water, what happened to them?
They floated to the right and came back to shore.
Okay, so they floated towards the cut over here? Okay, so why do you think they floated that direction?
Because the water is going in over there.
Okay, do you know what the name of that is? Yeah, do you know what the name of that current is? Okay.
Is it a current?
It is a current. It's called the longshore current. Okay, so can you imagine how they got that name?
Yes.
Yeah, it goes along the shore. Okay, so which direction is our longshore current going?
That way.
To the right, okay.
What did the result of this experiment teach us?
I learned that how it moves, the water moves in a certain way going towards the transit to bring settlements and other items onto the bay.
So, why is sand found in the bay?
They have sand in the bay because of the longshore currents that drag it across the point to the bay.
The Argos test a sediment sample and checked the salinity to compare it to what was found in the bay. They found that the sediment found on the beach was smaller and finer than what was found in the bay. The salinity measurement and the temperature is what helped them prove that the water in the bay was from the Gulf. The Gulf water salinity is the same as the bay water at about 24 parts per thousand because the flooding tide brought the Gulf water into the bay. So the Argos have learned how waves and tides move sand and sediments from one place to another in an endless process of change along our coastlines and bays. Hey, it's time for another question. I hope you're ready, because here it comes. What creates the longshore current at the beach? Is it A, tides, B, gravity, or C, waves? What do you think? The correct answer is C, waves. And if you got that correct, wave your hand. Nice job.
Okay, guys, so welcome to the Paleontology Hall here at the Houston Museum of Natural Science. So, do any of you guys know what paleontology is? It's a word we don't hear a whole lot in English.
It's digging, looking for dinosaurs underneath the ground for their bones.
Okay, yeah, that's part of paleontology, is studying fossils. And actually we have a pretty concise definition for what fossils are. Fossils are any remains or traces of prehistoric life. So just anything that shows us that something once lived and tells us that it was an organism there, that's a fossil. So fossils come in several different kinds. I brought some examples of them. This is a tooth from a baby mammoth that lived in Texas about 13,000 years ago. And this is made of this exact same mineral that the animal made. Nothing's changed about it. So we call this original remains. Our definition of prehistoric is anything 10,000 years old or older. And since that mammoth lived about 13,000 years ago, that fits. Okay, so here's another kind of fossil. And it turns out there's no footprints, nothing original left behind, but something really weird. There's these holes in this rock, and this is where there was an actual part of a skeleton from a marine animal, and sediments buried them, and then the actual skeletal parts dissolved away and left holes in the rock where that skeleton was. So nothing's left behind here, the original, but it's still a fossil because we can see that there were skeletal parts here. And if we actually took some plaster or latex rubber, we could fill in these holes and we'd come up with a thing that looks like this, which is a replica of the original, and that's called a cast. And not until about 540 million years ago do we actually see an animal that could make a skeleton, and that animal was the trilobite. And that's very important because before you have skeletons, hardly anything gets preserved because bacteria break down all those soft tissues. And once trilobites started making skeletons, they would live and die but leave their skeleton behind. So now we have a good fossil record of one kind of animal in the ocean. And very soon after trilobites show up, other kinds of animals like clams started making skeletons. So we start getting a very good fossil record. And for the last 540 million years of Earth's time, we've had lots of skeletons to tell us how old rocks are and what was going on in different parts of the Earth.
Finding dinosaur bones is no easy chore, and excavating them is difficult as well.
In a search for prehistoric life, Dr. Jim Westgate and his crew continue to dig for clues. Clues showing which dinosaurs lived in Mexico's Chihuahuan Desert 15 million years before they became extinct. After one day on the dig site, the team discovers a collection of bones. They believe the bones belong to a duck-billed dinosaur.
We'd found dinosaur bones in the state of Chihuahua before, so we went down just to try to figure out if they're mammoth or dinosaur or whatever, and turns out they're dinosaur bones. We got almost a complete duck-billed dinosaur of a genus called Critosaurus, and also associated carnivores, a relative of T-Rex called Albertosaurus, and some velociraptor-like little carnivores. And we actually have tracks of T-Rex fossilized, so we can see those. 40 feet long, pretty massive predator, whether he was a scavenger or not. And again, this is a great way to tell geologic time. He only lived for about 5 million years. Earlier forms of these big guys had three fingers on the hands. So we can see evolution and progress as that hand gets smaller. The fingers are lost through time. T-Rex went extinct about 65 million years ago with the rest of the non-feathered dinosaur extinction. So a pretty short lifespan, but he's known all over the world, probably the #1 fossil in the world for name recognition. So these specimens are from the age of mammals. They're about 40 million years old. And what's different about this horse than modern horses?
They're much smaller.
Yeah, these horses are much smaller than today's horses. And it's interesting, if you look at their toes, they have hooves, but instead of on one hoof per foot, they have 3 hooves per foot. So these are called 3-toed horses. So you can see how big it was to have trouble riding a horse at this time. But what did this saber cat not have any trouble with a horse at that time? Yeah, these saber cats were just the right size to eat these small horses. And the ancestor of this horse was called the 4-toed horses. And actually we have a jaw from this. This is from Laredo that we excavated. This is about a 42 million year old horse jaw. And if you compare it to this one, it's a little bit smaller. And this one had 3 hooves on the back feet, but 4 hooves on the front feet. But by the time horses became horses, they started with 4 in the front and 3 in the back. And through time, what happened to them? How many toes do they have today? So this one now, with the 4-toed horses, they had lost the thumb. So they had 4 toes on the front. Now they have lost the 5th finger, and they're walking on the 3 middle ones. The modern horses have lost the side ones, and they're walking on their very middle one. But we see remnants of these side ones, and if you hear about race horses break their bones sometimes, they call them splint bones, and they're these remnants of those digit 2 and 4, that they still have remnant support bones, but they don't actually have the flexible hooves and the flexible digits left. Yep.
Why would they have developed into one hoof?
This is 40 million years old. By 20 million years old, they're about twice the size, had longer legs so they could run faster. And if you're running through grass, just like if you're running through snow or anything that your toes may hang up on, the less resistance to that grass, the quicker you can go. And the ones who weren't able to figure out how to do that did what? They starved to death and went extinct. So yeah, so it's not always a success story. Most of them tend to go extinct. And today, probably only 1/10 of all species that have ever lived are extant. So 99.9% of all species that have ever evolved are now extinct.
Do different people have different theories of how dinosaurs went extinct?
Definitely. Lately there's been a big move toward believing there may have been a large impact from space that caused the dinosaur extinction. Before that, and even today still, people think maybe it was extreme volcanism out of India, mountain building changed their habitat, could have been disease, and right now a lot of people are leaning toward that impact, but it may have been a combination of all of those.
Today, the Argos have learned that these fossil bones tell us more than we would ever know about the Earth and its history without them, and that these bones are just one part of the fascinating study of geology, the story of life on Earth.
I like seeing all the reconfigured bodies of the animals and seeing the trilobites.
My favorite part was learning that some of the different bones of the skeletons and everything are used for certain things to help them adapt to their environment, help them catch prey and hide from predators and everything like that.
I learned today that all the fossils today aren't real.
I know that the horses have to get bigger so they can move faster away from the saber-tooth from not hunting them.
I think probably one of the more interesting things that I learned was just how things have developed over time within their species even. Like seeing how some of the horses developed from 3 hooves into 1 hoof, I find that very interesting, and seeing the environmental changes as well.
I'd have to say the most wonderful thing about today was being with the students and having them ask so many excellent questions. They came up with ideas and questions that I would never have thought of, so it was great to be with such a group of inquisitive students.
Hey, here's your final question, so make it count. What happened to horses' toes over millions of years? Was it A, they grew extra toes? Was it B, they lost all but 1 toe on each foot? Or was it C, their toes got shorter? The correct answer is B, they lost all but 1 on each foot. Sounds painful. So, did you get all 5 questions? You guys did great!
Thanks for coming to this year's JASON program.
Remember, JASON needs Argos like you for national JASON missions.
If you would like to apply to be a National Argo, visit the JASON website at www.jason.org for details. And be sure to come back next year for the next JASON event.